Hello and
Thank you.
welcome back to the second webinar series on Cellular Automata. Today is the final session of this series where Professor Pedro Paulo de Oliveira will deliver a talk on characterization of the elementary cellular automata with neighborhood priority-based deterministic updates. Let me first introduce our esteemed speaker. Professor Pedro is a professor in the School of Computing and Informatics, Universidade Presbiteriana, Mackenzie, Brazil. He has done electronics engineering from Aeronautics Institute of Technology, Brazil, and MSc in Applied Computing, National Institute for Space Research, São José dos Campos, Brazil. He completed his DPhil in Cognitive Studies from the School of Cognitive and Computing Sciences, University of Sussex, Brington, England. He has worked in several academic institutes. He was a researcher in National Institute for Space Research, a professor doctor in University do Vale do Paraíba, Brazil, and a visiting researcher in School of Electrical Engineering and Computer Sciences, University of Ottawa, Canada. He has joined as a faculty member of his university, where he is currently working, Universidade Presbiteriana, Mackenzie, Brazil, in 2001. Professor Pedro is also an esteemed member of several groups and societies like Brazilian Computing Society, Brazilian Society for Applied and Computational Mathematics, ACM, Mackenzie's Research Group on Natural Computation and Adaptive Computing System Engineering. He is also the chair of IFIP Working Group 1.5 and former chair of the previous Rhenium and co-chair of the 25th International Workshop on Cellular Automata and Discrete Complex Systems, that is Automata 2019. He is also member of editorial boards of the Journal of Cellular Automata, Complex Systems and International Journal of Natural Computing Research. His research interests are cellular automata, automata networks, evolutionary computation, natural computation, and artificial life. Now let me get the dais over to you, sir.
Oh, thanks. Many thanks, Kamalika, for this very nice introduction. Hello, everyone. Good evening, good day. Probably, I think for most of you, should be good evening, I presume. And well, it's a pleasure to be here. I apologize. This talk had been announced last month or earlier this month, but I had to postpone it. But fortunately, we're here, and many thanks, Kamalika and Sukanta, for having me here, for the invitation. I'll share my screen. Can you see it?
Yes.
Yes. Okay. So what I'm going to talk about today is a piece of work I have been doing with one student who is Thiago, is the second name here. He's my PhD student. All this work is related to his ongoing PhD thesis, and this is also joint work with Eurico Ruivo, who is my colleague at Mackenzie University. So this is to some extent work in progress, because we have just published the first part of this work, and but there's still things to do. So at the end, I will even ask for ideas about how to proceed. So this will be very welcome. This is about a form of asynchronous cellular automata, which we have been calling neighborhood-based asynchronism. The whole idea, well, it's important to emphasize that this is all about deterministic asynchronism. So it's all about defining a way of having, sorry, defining this form of asynchronism in a way that it would become a property of the rule. So this is the main, this will become clear as we proceed. So this has just come out, which is the first part of what I'm going to talk about. So what's the context? There's a lot of work in the literature about deterministic form of asynchrony by block sequential updates, which is the cell positions in a lattice are assigned some update priority. So you have a lattice of some size, and you create a partition of the lattice, and for the blocks of cells in this partition, you assign a priority. This block will be updated first, and this other block will be updated second, and so on. So, since this is related to the lattice, so the number of update schedules which are possible increase exponentially with the size of the lattice. So this kind of block sequential update is a bit difficult to handle in this aspect because it's linked to the size of the lattice. Nevertheless, there's a lot of very nice piece of works done with this. It's very useful. And here I'm only just illustrating a situation with elementary cellular automata 150. By the way, just opening a bracket, during this talk, I'll only be talking about elementary rules, right? Elementary rules, three cells, radius 1, which means that one cell can see one neighbor, the nearest neighbor from each side, which is, it's a space with 256 rules, well-studied, well-known. This is all about the elementary space we will be talking. So in this illustration here, on the left-hand side, I'm running ECA 150 with some random initial configuration of size 211. And this is the synchronous case, the synchronous evolution. And here I'm doing this block sequential update like that. In one time step, I update only the cells at even positions, and then the others, in the next time step, those in the odd positions. So I keep flipping these two scheme. So it's asynchronous, it's deterministic, and of course, as we would expect, the situation, the temporal evolution is completely different. And it so happens that this example is a solution we published 2 years ago. which is a solution to the global parity problem with ECA rule 150, which is the local parity rule, and with this nice update of even odd positions, and also the global parity problem, meaning that if there is the number of ones in the initial configuration is even, the temporal evolution leads to a fixed point of all zeros, otherwise to all ones. So this is just an example, and you see when the block when the update is generalizable like this one, okay, so you don't have this problem of getting this situation that's dependent on the lattice size, but in general, the updates are not generalizable. So this is the difficulty to handle this block sequential, this kind of update. And that was, in a sense, the motivation for what we did with the neighborhood-based update, as I will explain. So this is the paper that is related to that solution. So what's our point here? In the synchronous case, we can assume that all state transitions of a rule, in this case ECA 90, have the same priority. So they have the same priorities. But you could think of giving different priorities to these updates, to these state transitions. Like here, I mean that this state transition will be updated first, this other one, this in second, and so on. Oops. You could even have these two state transitions with the same priority. It's fine. But this is the idea. So instead of, so you assign an update priority to each state transition of the rule. And one iteration then refers to going through all the priorities in a particular schedule. So this is the original update in the previous slide, but it turns out that if you do this, you don't have to mind about all the state transitions. You only have to focus on the active state transitions. Like here, these are the 4 active state transitions of Rule 90, meaning that the central cell here is white and it becomes black. So there is the actual cell at issue changes. So it's active in this sense. So we don't have to bother about the other state transitions. So in this particular case, this would be the one possible neighborhood-based update priority scheme, right? And so this changes the whole thing in terms of it becomes more, even simpler. So just to give an example here, as of course, as we would expect, this is just an example. Here I have rule 90 with this lattice of with 100 cells. This is the synchronous update, and this is it's a sequential because every state, one of the possible sequential updates, because every active state transition is triggered in sequence. So the temporal evolution can be, of course, very differently. If we look in the state space, it's, you know, the thing gets even more evident, because here I'm considering all configurations with eight cells, and we can see that the state space is very different. Okay, so it turns out that if you want to work out the number of independent updates, there are some trivial conditions that you can visualize, that you can see in order to eliminate some updates, but this is trivial. The less obvious is that the number of independent updates, it follows what's called the Fubini numbers. The Fubini numbers, it's a combinatorial number, which is the number of ways that you have this competition with n competitors, and it's the number of all possible ranks in this competition, and if you allow ties between competitors. So this is a known concept in the literature, and what I have here in this table is you can have from zero active state transitions up to 8, and this is the number of independent updates given by these Fubini numbers. Here I have the number of elementary rules according to the number of active state transitions, and this is just an example. Of course, if you don't have active state transitions, you're talking about rule 204, which is the identity. On the contrary, if all transitions are active, you have eight state transitions, then you have rule 51, which is the conjugate. So it keeps flipping the initial configurations. And most ECAs have 4 active state transitions, 75 independent updates, and there are 70 rules. So if you want to then look at what would happen with every rule in the elementary space, then you would have to consider for each one every independent update, and that's what we do. I have to open a bracket here just to remind you about rule composition. So I have, in this notation here, I'm referring to rule 13 with two states. It's a binary rule with radius 1/2. Radius 1/2 means the neighborhood has only 2 cells, and it's just to give you this, to remind some of you about rule composition. So here I'm composing this rule with radius 1/2, and this rule is another rule with radius 1/2. So this means that if you have all possible configurations here with 3 cells, and apply this first rule, you would get this sequence of configurations here. So if you take these outputs and then you apply the other rule, then, then you would have this sequence of outputs now with a single bit. So the composition of 13 and 5 in the space refers to having, as if in one time step, you would go from the 3 cells to a single one, which happens to be elementary rule 187. So every time you compose the rules, the rule that you get in the outcome has a radius which is the sum of the radii of the rules being composed. So this composition, it does, these two rules do in 2 time steps what ECA 187 does in 1 time step. And I'm reminding this rule because this is essential, because it turns out that, well, let's see this example. ECA 90 again, with this update scheme. So the red state transition have priority 1, and the blue state transition have priority 2. So because there are two priorities, then first you would the red state transitions would be triggered, and then those with the blue, in blue. Well, but it turns out that these two rules are actually, if we consider them individually, this is CCA rule 72, which is assigned priority 1, and ECA 222 with priority 2. So it turns out that the composition of these two rules is a rule with radius 2, with this number, and so what happens is that any rule update pair actually is essentially asynchronous CA. So when we reached this conclusion, it was kind of frustrating to some extent, because we started with some asynchronous scheme, but in its bottom, in its deepness, it's actually asynchronous CA. There is asynchronous CA that is associated to any rule and rule update pair, considering neighborhood based. Anyway, we still have this facility of defining the asynchronism in that way, which may be helpful in some kind of application. Or I would love to hear some comments on the possibility of doing some application with this scheme. But at the end, we can ask, okay, now we have this space of synchronous CAs that come from this scheme. That what would there be in this space? So this is the way we proceeded, and So it's interesting in itself as as a dynamical system, as a discrete dynamical system, as a mathematical object, and so on. Okay, so well, this is just a picture showing that the rules actually are the same, right? So we can analyze the entire space of rules and the independent updates by getting these synchronous associated CAs, right? And this set of synchronous CAs, each one has its dynamics, which I'm calling here NP dynamics, which is a neighborhood priority based dynamics. So the NP dynamics is actually one NP dynamics is actually the synchronous CA that one of those that we get. So for all the possibilities in the elementary space, we have these numbers of possible NP dynamics, and the number of NP dynamics is smaller or equal to the number of updates, as we can see here. And this happens for various reasons. So let's see some examples. Here I have ECA 11, which has 5 active state transitions. And then because of this, there are 541 independent updates. Among those, these two here are 2 examples. These are independent updates. However, if we consider ECA rule 11 with the first update, it refers to this composition of these 2 rules, all these ECAs, and with the second independent update, we have this other composition. However, if we perform the composition, then we realize that these 2 compositions lead to the same radius 2 rule with this number. So because of this, not only because of this situation, but it turns out that ECA 11 has only 389 dynamics, whereas the number of independent updates is 541. So this is the first possibility for the number of NP dynamics become smaller or equal to the independent updates. Here's another example now with elementary rule 2, also 5 active state transitions. These 2 updates are 2 of them. But it turns out that ECA rule with this lead to this composed rule with radius 2, and these are the update leads to this other, different from the first one, radius 2. However, these 2 rules are equivalent by reflection. Okay? This you can define a conjugate, a reflection, and a reflected conjugate of the rule. So essentially, they are the same, which is not apparent from looking at the rule numbers themselves. A third example, again with ECA 11. Sorry. And by relying on further two independent updates. ECA 11 with this update leads to the radius 3 composed rule with this big number. ECA 11 with this other update leads to this other rule with radius 4, which with this even bigger number. But it turns out that these two rules, radius 3 and radius 4, they have dummy neighbors. So they are, although they have been obtained in these larger, in these spaces with larger radii, they can be, they are also happen in smaller, with smaller radii. And in this case, these two rules refer to this rule with radius 1.5. Radius 1.5 is has four cells in the neighborhood, and it's ill-defined in terms of reflection. So we can add an additional dummy neighbor just to have the rule symmetrical in terms of the number of cells in the neighborhood. And they lead to this radius 2 rule. So these are the kinds of things that make the number of NP dynamics smaller or equal the number of dependent states. So the procedure we followed to compute all of the dynamics and getting rid of these additional redundancy, it goes like this, or it went like this. So these are the rule, each rule of the elementary space. So I'm giving as a reference, taking one rule, so just the first one, ECA rule 0. So for each independent update of this rule, we compute the corresponding synchronous CA. Then with each one of them, we perform this rule radius reduction that I hinted at before by elimination of dummy neighbors. And then when required, adding an additional dummy neighbor so that we would have a symmetrical neighborhood. Then for each one of them, we construct the equivalence class in terms of reflection, conjugation, and conjugate reflection, and get the representative of each one of these classes of dynamical equivalence. Eventually, this leads to some duplicates. We get rid of them, and then these are the final number m of dynamics associated with this rule, which is smaller or equal than n. N is the number of independent updates. So this procedure is done for odd space, and also what I showed in the previous slide has to do with each individual rule. But if you consider all the rules together, then you can, with all the representatives that have been elicited, as I mentioned in the previous slide, they can be grouped in things things like ECA rule 0 is equivalent to ECA rule 255. So you can join the elicited representatives of each one into the same class. And if you do this and remove the duplicates, then you would have, for each class, we have 88 classes in the elementary space and no more information about the individual dynamics. And so we can have this situation analyzed in terms of the classes. So if you do this, we get this table and some remarks that can be done. You can get the NP dynamical rules, the synchronous CA with radii up to 8. Considering the individual ECA classes, there is this number of distinct NP dynamics. If you take the classes together, of course, the number decreases because of redundancies. We looked at all of them, and parity preservation is in the whole space is added. There are rules in the elementary space which are parity preserving. So if we consider this set of NP dynamics, there is one additional scheme that is parity preserving. There is no parity problem solver. And no further number conserving dynamics other than the synchronous case. So we thought that it would be worth looking at because, okay, we have all this data, and okay, is there some structure in it? What kind of property can we make sense of in this space? So these are attempts that we tried, and so this is the kind of thing that I would love to hear from you in terms of which other thing we could look at in this space. Okay. Up to here, this is the piece of work that is in the paper that just came out. What's next is thing we are doing right now, and specifically actually for the book that is being edited by Kamalika, Sukanta, and Suvik. And the departing point is, what if we impose the cells to be updated only once per iteration? Why is this question? Because if we take, for instance, rule 90 with this update in the original scheme that I've been talking about up to now, you can have a situation, this is just a trivial example, very simple, in which we see that, well, with priority 1, these two cells are updated. With priority 2, then this cell, which has just been updated, it will be updated again. And then with priority 3. So the question is, what if we define another scheme of update in which we would only allow a cell to be updated only once? So this would be the situation. It turns out that priority 2 in this trivial example wouldn't even be triggered, and the final configuration would be just one bit different. The right hand, the one in the right hand extreme of the configuration. So this is what I'm changing now to this other scheme in which each cell is allowed to be updated only once. And it turns out that we can see this situation in terms of the same one as before. In terms of composition of rules leading to synchronous CA, but instead of 2 states, we would have to consider 4 states per cell. So what is the situation? So what we do, we associate the original states, 0 and 1, to a corresponding inactive state. So 0 would be associated to this 0 prime, 1 to the 1 prime, with these colors. If we do this, so the idea here is that with these inactive states, so when one cell is updated, it enters this inactive state, so that it won't be updated anymore. This is the idea. And the consequence of this is that we would have to extend the original set of active state transitions of the original rule into a new set that would take into account these auxiliary states. So these are the four original state transitions, active state transitions, that we then have to take into account the inactive state transitions. I'm sorry. And then instead of handling 4 state transitions, we will then have this extended set, in this case with 16 state transitions. But now we would then have a CA with 4 states. Okay, so this is the idea. So what we do with this transformation, we would perform. This is the very same example that I showed you 2 slides before, but now in color. And so this would be one iteration after the association of the active states to auxiliary inactive states. And then at the end, we would have to return back to the binary situation, because these 2 additional auxiliary states, they would just be a way to handle, in a sense, to provide the right perspective to what's going on. And then we would have to get back by using the opposite transformation, which can be seen as the application of this rule, number 68, with 4 states, and radius 0, which is just, just considering the cell itself, getting back to the original binary states. Okay, so this is the way we do. So every composition at the end would have an additional cell, which is this one, to be to finish the composition, and it wouldn't add it wouldn't increase the radius of the rule at that point. So if we do this with rule 90, in the case of one single priority, this would lead to this 4-state radius 1 rule with this number, which would then be composed with the rule I just mentioned. And so the result of the composition of this rule with the rule with radius 0 is the corresponding NP dynamics for this particular rule 90 and a single priority. Of course, this leads to, since we're talking about four state, and as we increase the number of priorities, you can get very big rule numbers, very big rule numbers. And so by performing the same kind of procedure that I mentioned and illustrated in the first case of multiple updates, this is the figure, the data we get. These pending situations, I doubt they are still running in a supercomputing facility in Brazil, but I doubt they will finish, and I'm not sure they will bring any information that might be worth that would highlight some of the properties we've been looking at. But they're running, and anyway. So if we compare the two situations, I'm finishing right now. Well, very soon, 2 slides, I think. So if we compare the two situations, we have 23 CA classes with the same number in both cases. 10 CA classes have more NP dynamics in the case of 1 update per cell. And majority, 41 ECA classes, have more dynamics in the case of multiple updates, which is not very surprising. This was our intuition that we would have, since the 1 update per cell is more constrained, so the number of dynamics would reflect that. And in general, well, in total, multiple updates per cell has richer dynamics. However, we didn't have the chance yet to try to make sense of what happens that some classes have the same number of NP dynamics, some classes with 1 update per cell has even more dynamics. And this is questions we know are in our pipeline to address. And also, even if you consider the case where the number of dynamics is the same, is there an overlap between the dynamics? So we didn't look at all about this. Another observation is that smaller radii, we see here the number of dynamics with the various radii. So as you see here, those with 7 and 8 are still pending. But we see that the number of dynamics with radius 1 and 2 for the multiple updates, they are smaller but from 3 onwards, they increase a lot. They increase relatively a lot comparing to the number of dynamics with only 1 update. And although there is some intuition about this, we would like to have a better grasp on what's going on why this happens. So, what's next? Well, we want to make some further analysis of the structure of NP dynamics in each individual case and also in relation to each other. Well, one thing we've done is that we looked at the scheme with only 1 update per cell and no number conserving rule does exist. With the multiple, of course, those with the synchronous update would be preserved and nothing new happened. But now when we restrict the situation to 1 update per cell, there are no number conserving rules. So any ideas about which kind of thing we should look at and how to make sense of the structure of these spaces? So I would love to hear today, or if you have some idea after today, so I would be pleased to discuss with this, and maybe there is space here for some collaboration. And okay, many thanks for your attention. That's what I intended to tell you about. Thanks a lot.
Thank you, sir. Here, Shovik has already asked some question. Shovik, can you please speak out?
Sorry.
Yeah.
May I, Suvik, just a moment, please. May I ask for someone who's asking to speak slowly, please? I'm not quite used to your accent, so.
Yeah, Shovik.
Thank you.
So with the first proposed model with that NP dynamics, you have mentioned that at the end there are 88 rules which can uniquely represent this set of rules which comes from 256 ECA rules. After conversion, we can get 88 rules which can represent. And when we do some left-right reflection and 0-1 complementary with 256 rules, we can also get 88 rules, minimum representative rules, which is noted in one paper of Packard and Lee at 1990. So these two numbers are same, 88 minimum representative rules also there, and after doing this after applying this Cellular Automata model with NP, we also get at the end 88 rules which can catch the dynamics of all rules. So is there any connection between them? That's my curiosity.
You were asking about the connection between the compression we did in the space with which other thing?
I'm saying that for ECA we have 256 rules and there are 88 rules. These are the minimum representative rules which can represent these 256 rules. So here also from this 256 rule, you are getting a set of rules by applying this system, and again it is possible to club it with that 88 rules. So these two numbers, 80, both cases are 88. So is there any significant meaning of that, or
Well, I'm not. I still sorry, but I still
Maybe I
I'm
can
still
try.
not sure. I can.
Sir, he is asking that in case of ECA, synchronous ECA, there are 88 minimal rules, right?
If you are asking whether the why the same number,
Yeah,
why
why
the
the same
88
number?
is okay. Well, this is explained in the paper actually. There is a formal part in the paper that addresses exactly your question. So it's all well put there. So I would have to ask you to see the details in the paper. But yes, your concern is well founded, and so it's being explained in the formal part of the paper.
and I have another question. Can I ask?
Yep.
Yeah.
Yes.
Yeah. So what happening is that what you have shown in case of deterministic asynchronism, this word deterministic is important because when we applying deterministic asynchronism, some other rules, maybe with other radius or something, can able to catch them. So my question is that until and unless we are introducing actual asynchronism like noise, uh, uh, then with deterministic asynchronism, can we get rid of from that others can able to catch them? My question is clear. When we add noise in um, for for introducing asynchronism, like the already established model like alpha asynchronism, beta asynchronism, when we put some noise, then is it possible to catch these dynamics of rules by using, because there are lots of robustness in the dynamics. So this question is for like that, is it possible to catch this type of robust dynamics with other rules? This is the first question. And second question is that if we apply deterministic asynchronism, it is is it possible that we always get some rules which can able to catch? So these are two questions are connected. If my question is clear.
If well, let me try. Well, if you add noise, the situation will change dramatically. Maybe you're thinking whether all the NP dynamics we get in the deterministic case would be included in the set of dynamics that we would get in the noisy version. Right? I think we will see. I think so. Well, I think you will see them. Yes, they would be a subset of all the possible dynamics that you would get in the noisy situation, if that's what you're asking. Yeah. Okay. Thanks.
Okay, any other question?
I have a simple question. Achha, any application you have thought about the model you are proposing? So any application of that one?
I would love to have. I would love to have one. We initially we had this intuition that when you have this this natural system, like chemical reactions, for instance, they would be imagine you have a chain of agents related, each one to some local chemical reaction. So our intuition in the beginning is that, well, each one of these agents, they can do their thing as locally. I mean, their nature would define what they should do, and not necessarily this situation where you would have it seems to us that a system would be freer to do its thing in a scheme like the one we did, because it's their priority of doing that thing. Of course, again, you would have some general control that would assign the priorities, but maybe the timing that this thing would be triggered could be modeled by this priority. So this was the kind of intuition we had, but honestly, we didn't see, and we didn't look for at least yet some kind of possibility. But I particularly would like very much to see the possibility of analyzing a natural system of some sort from the perspective of this kind of model. I would love that.
I will, I have also one point. I would love to see the change of dynamical behavior, like a chaotic system, and if you do the composition like this way, what kind of effect we can get, or computational universality, if we talk about, what kind of effect we can get if we compose in this way. Have you thought about this?
I mean, the composition is a consequence. It's not something that we can not do, because it's intrinsically associated. It's a consequence of the model. So, not sure I'm getting your point, but the composition is just a way to elicit the resulting dynamics, right? In a robust way. Of course, you could try to get the dynamics by doing a sample of configurations and keeping everything in the looking at and analyzing the temporal evolutions, but that wouldn't be enough. So you would have to consider progressively larger configurations. So the whole thing about the composition is that it comes naturally from the model. It's to my mind, it's the right way to think about it.
I actually wanted to know about the computational ability of your model.
Well, computability. Well, you see, we try to see whether the possibility of any rule in the space would be able to compute the parity, for instance, well, in the first model, we didn't find any. We found the possibility of rules with parity preserving, but not enough to become a new algorithm for computing parity. So my student was also trying to see whether any of these rules would be able to compute density. But, well, they wouldn't compute density, of course, but how well they would compute density if they would have some particularity that would turn them or turn one of them into a good density computer. So the kind of, this is actually, Sukanta, this is in the core of what's next. Which kind of, which kind of property, which kind of computation ability that we might be able to identify in this set. But,
right.
yeah. Okay?
Yeah, right. Thank you. Thank you.
Thank you.
Hello.
Yeah.
Wait, mobile. Sorry. So, sir, I have one question, sir. Who told me that in case of NP dynamics, what you saying, sir? If you update single point, there is no chance of getting number consuming cell. So, is there any possibility if we update more than one cell to get number consuming cell, sir?
Sorry, I think I missed your point. Are you asking about number number conservation?
Yeah, number conservation, sir.
Number
told me
conservation
that,
in
sir,
case of multiple update.
Yeah, if we single update, there is no chance of getting number consuming CA. So if we consider more than one cell update at a time, then is there any possible to getting number consuming CA?
Are you making the point that one update per cell cannot be number conserving?
Yes.
Yes. Well, I don't see the argument, but I would be willing to see exactly why would this be the case. If you, well, at some point, maybe by writing instead of. But thank you for your observation. So you see this argument. You see this argument. Okay.
Yes, sir. Actually, in case of asynchronous CA, I did this work that if we update a CF cell, just like using some update pattern. So for a single cell, it is not possible. But if more than one cell we update some using some update pattern, there is chance of getting some number consuming CA. So I did this for asynchronous CA. So that's why I'm asking.
Okay, anyone else? Sir, you have observed.
Kamalika, just
Yeah.
Dipanika.
Yeah.
Okay, Professor Pedro, this is actually the question that Shukanto asked. I was thinking that is it possible that as an application, I was thinking some abnormal growth or something, because it's a synchronous thing and one cell is only evolving in a synchronous way rather than other. So can we model that thing? One probable application, as Shukanto was asking, thinking that since it is a asynchronous evolution, that one or more cells that will evolve, can we model that abnormal growth or something? Because if it is abnormal growth, some cells actually evolve more, that grow quickly, and then other. So I think very nicely we can model that thing.
Right. So you're suggesting that an application would be some growth of
Yes,
something?
Yes.
like a growth of
Yes.
like fire in a forest, things like that, for instance?
Even I'm more optimistic. I'm thinking that abnormal growth, like tumor growth, that was linear C was very old. That one paper was there, but there mainly the restriction was that since all are evolving parallelly, so it was difficult. So now your this nice structure, this characterization, I was just immediately it came to my mind. For some cell, it is asynchronous growth. So some cells are actually evolving very fast, and some cells are actually not. That second slide what you have shown. So then we can easily map to that actually tumor growth or abnormal growth. So and we can probably overcome the restriction that what earlier paper had, very old paper that some tumor growth model using cellular automata. So probably because just it came to my mind, probably I will read your paper. I think it is available in net, and then I'll be talking with you. Just as an application, it came to my mind. And what you are telling, forest, etc. also. But probably we can see that part. Shukanto, I was thinking that type of application when you asked.
Yeah.
Okay, Professor Pedro is a very nice different type of characterization, probably different type of modeling and application also we can explore with your characteristics. Thank you. Thank you.
Thanks for your comments, Dipanvita. Actually, I presume this is being recorded, so I'll re-listen to all your comments later, just to make sure I understand correctly.
And I will also read the full paper, and then because it is available in net, no, the full paper.
Yes, it's published.
Published. So, okay.
Yeah.
Sir, I have just like one curiosity. How did you find the synchronous CA associated with your this multiple update pattern?
How did I find what?
The synchronous one associated with your update pattern.
With one update per cell?
No, this your the scheme for your scheme for both the schemes. For both that, how did you determine that this particular synchronous CA will represent your dynamics? Have you tested all the CAs and then you have decided, or?
No. It's not necessary, because it's a direct consequence of the definition of each rule and its update pair. Its update scheme. So each pair of rule and its update scheme can be regarded as this synchronous CA. So the dynamics has to be the same. It doesn't have to be tested.
Okay.
So
there is an algorithm. So we can think of it.
Yes. Okay.
And what about the other kind of dynamics, like you have seen for number conservation? What about the reversibility or chaos, such kind of behavior? Have you seen if they're changing?
No, this is yet to be done. Yeah, like partitioning the space in terms of the dynamics into the 4 Wolfram classes, for example. We didn't do this. It's it's within the what's next.
Okay. And same is for this whether computably universal CA exists or not. That also in this what next group. whether
Sorry?
like ECA 110, some other rule like ECA 110 will be there in your scheme also, right?
Yeah, well, it's there to be
In what case?
found, if any.
If any. Okay.
Sir,
Thank you.
I have another question. Can I ask?
Yeah.
So, is there any hope of solving density classification problem by using this model? Because I'm asking that is there
No.
any hope of, because the same transition function is responsible for blocking the local consciousness. Same is also responsible for getting the global consciousness. So, with giving priority, is it possible to solve density classification?
Well, with the first scheme, it's not possible because it's a binary CA. Other dynamics are based on binary CA. With the other scheme, where you have the auxiliary states, then if we just consider that this possibility of solving binary the binary density with a 4-state CA, in principle it might be possible, because although I have done some experiments trying to find a solution by evolutionary means with the solution of the binary problem with the 4-state CA, but it was done with an undergrad student, and we didn't see anything useful. But from this perspective, it might be possible in the second case. But if we think in terms of the restriction of one cell being updated only once, then there might be an argument that would prevent it. To be honest, I don't have a clear understanding about this. But in terms of the space of 4-state CAs, it might be possible.
And another, I have another question actually. When a question means observation is that. So my another observation is in the second model. You have said that when a cell updated, in the next step, that same cell will not update, right?
Yeah.
Yeah. So
in the same iteration, it's allowed to be updated only once.
Only once, and if it is updated in the next iteration, it will not be updated. Once it is updated in the next iteration, it will not updated, right?
It can. In the next iteration, it can be updated. It cannot be updated in a single iteration. It cannot be updated more than once. Okay.
So actually, this actually related with the old Gilonke's work of atomicity property of modeling distributed systems. So, is there any future direction in that way? Because when Gilonke introducing asynchronism with this atomicity property for modeling distributed systems. So here also in the second model, we can see this atomicity property. Gilonke's work is very old work. Is there any future direction of model distributed system by using this atomicity property? So that is my observation actually.
Are you asking or are you commenting?
So I'm asking also. That thought comes in my mind. I'm asking also.
Well, yeah, it's. I mean, it's too vague at this moment to see. It might. Yes.
Shovik, you write to Pedro regarding your observation and points. Okay. Yeah, maybe we have to
Okay,
conclude.
so
Yeah.
yeah, so thank you, Professor Pedro, for giving this nice talk. Thank you so much. And you were right. You just indulged us to ask you lots of questions. Thanks for that also.